Imagine yourself by the coast, listening to your favorite playlist on your portable radio. Suddenly, an ear-piercing swishing sound is blasted on your radio, followed by loud radio static. You search for solutions to overcome the static. You remember a common stereotype that when the length of antenna is longer, the message conveyed will be clearer. Hence, you increase the length of the antenna. You notice that there was a brief moment where the music was the clearest, but it wasn't the antenna's maximum length, which contrasts popular beliefs. You go back on your phone to find videos explaining this concept. You find a video titled Optimal Length of Dipole Antenna Explained.
What's the science behind the optimal length of dipole antennas? This is a dipole antenna. It has two main parts, the antenna sections and the feeder. The antenna section is made of two identical conductive elements on each side. The feeder is the cable that connects the antenna with the radio transmitter. An antenna works as a receiver when electromagnetic field hits it. After the wavefront ends meet at a single point, the separation and propagation of the wavefront happens. This varying electric field will automatically generate a varying magnetic field perpendicular to it. It will draw electric field intensity variation with the distance. You can see that the wave propagation is sinusoidal in nature. The wavelength of the propagation so produced is exactly double that of the length of the dipole. Let's use an experimental study into the effects of the length of antennas on the signal-to-noise ratio of received radio waves as an example. This is the setup used in the experiment. A 400 Hz audio file is transmitted at 145 and 433 MHz respectively, using the walkie-talkie setup. The radio waves are then received by the makeshift dipole antenna 10 meters away, made of the metal strips at the antenna section and a coaxial cable at the feeder, which is connected to the MacBook. Researchers are then able to collect and calculate the necessary data using the Qubit SDR software on the MacBook. From the data collected, we are able to plot a graph about the correlation between the length of the dipole antenna in millimeters and the signal-to-noise ratio in decibels for 145 MHz and 433 MHz respectively, where the y-axis is the signal-to-noise ratio, while the length of the antenna minus half of the wavelength is the x-axis. From the graph, we can conclude that as the length of the antenna minus half of the wavelength increases, the signal-to-noise ratio, or SNR, will decrease for both frequencies. The data collected found that the signal-to-noise ratio was the highest when the independent variable was 0. This proves that the hypothesis is correct. This is because of the formula of the optimal antenna length. The antennas resonate differently for different frequencies at different lengths. This proves that both hypotheses are generally correct. The researchers concluded that to get the optimal length of the antenna, the formula lambda over 2 can be used. They also stated that using UHF is better than VHF bands, but could not explain why due to the limitations. This research validates the formula for the optimal length of the antennas. They also contribute to the UN Sustainable Development Goal 9 and can be shared with professionals when designing antennas.
We would like to thank these sources for their contributions. This research was conducted with the support and guidance of these individuals.